Welcome. I'm Dr. Jeff Hanson, founder of WaveForce Technologies and the original developer of the Wavector and XWaves applications for ocean wind and wavefield analyses. These software apps have been used for over 30 years by scientists and engineers around the world for such applications as wind and wave climate studies, extreme storm recurrence intervals for offshore design, providing inputs to offshore structure fatigue analyses, and quantification of forecast and hindcast model errors. Today I'll give you a brief tour to show you how these software packages can help you extract the most from your wave measurement and model results. Although I'll be running XWaves for this demo, both packages share the same user interface and support the same data types. The key difference is that XWaves includes several additional tools to support offshore planning and design. During the tour, I'll be sure and tell you what is included in each application. Let's get to it. Okay, when you first launch the program, it opens up our splash screen. Up here in the top left, you have access to a series of pull-down menus that provide access to all of the system functions. One thing you might want to look at first is our fully online help utility that explains every module, every command that the system offers. Next, you might want to load some data. As you can see from this list, XWaves and Wavector can read in data from a wide variety of instruments and numerical wave models, as well as some generic formats in case you have data from a source that we don't support. We're going to open up a process file that I've already loaded in. This is from the National Data Buoy Center, the Monterey Bay Buoy. Loading data opens up our data view window. This is a powerful module for exploring your data set. You'll see a series of plots and displays that are fully configurable. For example, here we have a time series of wave height at the bottom, as well as 3 different representations of the wave spectra and a data summary. I can easily save different plot layouts. For example, perhaps I just want to look at time series of wave heights, peak periods, and peak directions. Maybe I want to see the winds. Every plot title is actually a pull-down menu of all the available plots. Here we've replaced the wave direction with wind vectors. Another nice display to look at, one of my personal favorites, is a spectrograph display. Here on the bottom, we have contoured wave energy as a function of frequency. And you can see the time series evolution of the different wave trains. For example, if I click here, we can see that we have an instance where we have 3 separate wave systems evolving through the area. Next, we'll be showing you how our powerful wave partitioning algorithms can separate out and track these wave systems individually. Okay, but first you might want to do some data editing. We have a powerful data editor that allows you to smooth records, subsample files, change the resolution of your spectra, append and subset files, remove records, and even rename the dataset. This gives you a lot of control over getting your data into the form needed for the types of analyses that you're doing. I've already smoothed this data over 3 hours, which takes some of the noise out from the measurements. Now, how do we separate out our wind, sea, and swell wave components? As you can see, we've done in the plots up here. Well, that's done with our Wave Systems module. Opening up that module gives you a powerful tool for partitioning your data, separating out the wind, sea, and swell wave components, and tracking these over time. Running this module opens up the Wavector display. This is a powerful insight into the evolving nature of the wave systems in your data set. In this Wavector display, each arrow represents a single wave partition. Wind seas are shown in black, swells are shown in colors. The base of the arrow shows the wave period. The direction is the direction towards which the waves are rolling, and the length of the arrow is proportional to the wave height. As with the other displays, we have the capability of bringing up other types of plots, such as the wind vectors. And here you can see the correlation between the wind waves and the evolving winds. Going back to our data view module brings up a whole new library of plots to explore, showing how the wave spectra are divided into individual wind, sea, and swell components. Here's a case where we have those 3 wave systems, and you can see it's identified this higher frequency one as wind sea, and a primary swell, and a secondary swell. This is the corresponding one-dimensional wave spectrum, and here's a look at a Cartesian view of the directional spectrum with the 3 wave components. How do we get data out? We have a very important tool for you. It's called the Export Wizard. The Export Wizard first allows you to view all the available fields. Like here's your basic wave statistics, the wave system fields, like the heights, periods, and directions of the individual sea and swell components. And if you've done more processing, like I've already run the spectral fit module here, and you can see we get a lot more data available. So you can select the fields that you want to download, and you can select the type of file you want, whether you want ASCII, Excel, map file, or CSV. What kind of information you want to put into the header, like the field descriptions, and click Run. And now we can go and open that file. This is a CSV file, and you can see that we have nice column-oriented time series data of the heights, periods, and directions, which were the output parameters that we had chosen. So it's really easy to get data out. You can get all of the wave system information out. You can get all the statistics. Pretty much anything that's calculated within here, you can export into a file or a table. Now that we have the wave systems, we can look at the wave system climatology. Here, for example, are height, period, and direction histograms. Really nice to show how we have two different modes to the wave spectrum here, with a dominant swell component coming from the south and a dominant wind sea component coming from the northwest. Nice table here showing the means and extremes and standard deviations of the different wave parameters. What we've covered so far shows all the capabilities within Wavector and about half of the capabilities within XWaves. For more advanced engineering studies, such as designing offshore structures, shipbuilding, etc., you need the more advanced capabilities within XWaves. So let's have a look at some of those features. Here we are back at our Wavector history map, showing the time evolution of the various wind, sea, and swell systems that have propagated through the measurement location. Of course, these waves have traveled from all types of distant weather events. But where were they? Can we estimate them? We actually can, using deep water linear wave theory, which has been built into the swell map module. The swell map module opens up as a map showing the estimated locations where each of your swell systems were generated. Now you have a lot of capabilities here. There's the ability to pan and zoom. Here I've added a data layer showing bathymetry. We have different map projections that we can look at. Here I'm going to look at a satellite view, which gives you a nice perspective of the global Earth. Now we can pull up a lot of information for each of these events up here in the options. For example, let's take a look at event number 8. That seemed to have traveled maybe the farthest. This is the Southern Ocean swell that's come up all the way to the Northern Hemisphere. We can see that it originated on May 20th, which is before the time period of these observations. Traveled 7,600 kilometers at an azimuth of about 181, almost directly south to north. Now let's take a look at one of these events up here, for example, event 13. Event 13 originated on 25 May, traveled about 1,100 kilometers at an azimuth of about 300 degrees. All these data can be exported into a table to give you a full collection of the details on your individual swell events. And you can go back to the Wavector map and actually see what portions of the data each of these numbers correspond to. But keep in mind, it is an estimate because it is using deep water linear wave theory, which is an approximation of how waves propagate over the ocean. We have some publications where we have verified the validity of these estimates, and they can be quite accurate. You can even output the results to a KMZ file for import into Google Earth. Okay, the next module we're going to take a look at is spectral fit. The spectral fit module is used to compute essential parameters often used for offshore structure design and fatigue analyses. It includes several different model fit options for the partitioned wind, sea, and swell energy frequency and direction spectra. Running the module opens up a new library of plots for the data view module. The results include statistical evaluations of all fit parameters, and of course, you can export the results to a convenient fit parameter table. The sea-state module conducts a wind and wave extremal analysis of multi-year storm frequencies and intensities. It's often used for designing offshore structures such as wind farms and oil platforms. Here we've loaded a 42-year dataset to allow me to demonstrate to you the power of this new module. It performs automatic wind and wave storm peak extractions and then applies several different recurrence interval models for return period statistics including directional sector analyses. All the results can then be exported to a comprehensive set of tables and graphs. Okay, finally we have the Evaluate module, which is actually my most favorite module within XWaves. It allows you to statistically compare two data sets, whether they be two sets of measurements, or you want to validate the performance of a model, or compare two models together. Here we have the model results from Hurricane Sandy at the location of NDBC buoy 44008 in the Atlantic Ocean. The observations are solid lines and the model results are in dashed lines. We have wave height, wave period, and mean direction. To run the Evaluate module, I'm just going to click on this action button up here, and it's going to open up the template that all the modules have for setting up the analysis. You get to pick your baseline data, your evaluate data that it'll be compared against, and you can do analyses on the entire data set, or if you have a large data set, multi-years, you can do analysis of just the peaks. You can even evaluate wind, sea, and swell wave systems if you've already performed spectral partitioning, or if you haven't, it'll perform it for you. Now, I wanted to remind you, you see this question mark up here in the top right. All of our templates have this, and it will open up the exact pages that correspond to the part of the program you're working on. For example, here's the help pages for the Evaluate module. We have an overview that provides all the details, including the equations used in calculating all the metrics. Once the Evaluate module completes processing, we can now see our statistical results. For example, over here we have scatter plots of wave height and mean wave period. We can even bring up an error table for each of those parameters. For example, these are the bulk wave heights, showing us the bias, RMS error, scatter index, and correlation coefficient for this data set here. Likewise, we can do the same for wind speed, wind direction, wave height, wave period, and wave direction. It's a really powerful tool. In closing, the Wavector and XWaves software applications have been used by most of the major offshore energy companies, as well as a multitude of offshore consultants, government organizations, and universities around the world over the last 3 decades to solve their most critical offshore engineering and oceanographic problems. For additional details, sales, and contact information, visit our website at waveforcetechnologies.com. And thank you for watching.